integration techniques. So we'll look at the basic ideas again, remind ourselves of this, and then we're going to look at a use of integration, these definite integrals. So that's something that you've seen before. The integral of 3x with respect to x. So this symbol here means integrate. 3x, so that's what we're integrating, that's the function 3x. This is telling us what the variable is. So x is the variable in this integral. So that's what I'm integrating. Any other letter that appears in here will be a constant. So if I say to you, for example, integrate, so therefore integrate bx squared with respect to x, this is telling us that the x is the variable, so that's what I'm going to integrate, and b is some number, some constant, I just don't know what that is. So b is a constant. And when you come to look at the assignment questions, that will come into play, because you need to consider which of the letters inside the function are constants, which is the variable, and then the idea is to try and find out what the value of these constants is. So identifying the variable is important, and that's what tells us there. Often that's a t, because we integrate with respect to time very commonly with functions, because we're often interested in how functions vary with time, so you integrate with respect to time. To do this, you use a table of standard integrals. So just like when you differentiate, you refer to a table of differentials. So to do this, to integrate, we use a table of standard integrals. SI for standard integrals, often referred to like that. So that makes it sound very straightforward. You just look at the table, find the right one, and that tells you what the answer is, as we'll see. The difficulty with integration is getting it to look like one of those standard integrals. So we'll start off with some that are quite straightforward, and in fact at the past part it will be pretty straightforward, but those of you who are going to carry on maybe and do some more work next year will see that actually the real difficulty of integration is when you've got to try and get it to look like these things. So it starts off easy but then gets more difficult. Right, so we're going to now put down the table of standard integrals. These two laws of indices will be handy to remember, so bear those in mind. If I've got an inverse, it becomes a negative power, and this root thing becomes x to some fraction. So the function, the first one, the most common function that we're going to use, will be some constant a times x, which is our variable, to the power some power n. So it could be a fraction, it could be a negative number, some power. When I integrate that, can anybody remember what you do when you integrate? That's when you differentiate. So what do you think you do when you integrate? Add 1. So it becomes ax to the n plus 1, and then you divide by the new power, n plus 1. And that might, for example, the one that we had at the beginning of today, 3x squared, becomes, if we add 1 to the power, so that becomes 3x cubed, add 1 to the power, and then divide by the new power. So it becomes 3x cubed over 3, which we can then cancel down to give us x cubed. So that's an example of the use of it. As a check that you've done it correctly, if I differentiate this, the x cubed, if you remember what you do when you differentiate, you bring the power down, so that will be 3, and take 1 off the power, which takes us back to here again. So in other words, it undoes what we did before. So that's the most common one. Right. Then we have these trigonometric functions. So we're only going to write down the integrals for the sine and cosine. There is also a standard integral for the tangent, and if we use that later on, then we'll add that to our table, but for now we won't put it in. Sine AX becomes minus 1 over A cos AX. So sine AX becomes minus 1 over A cos AX. For example, 6 sine 3x equals minus 6 over 3 cos, which is minus 2 cos 3x. Next one, A over x. This is another standard integral that we use quite a lot. Turns out to be the natural logarithm, a times the natural logarithm of x. So that's an ln. That's ln. No, because log is the log to the base 10. This is the natural logarithm, which is to the base e. So, for example, 3 over x becomes 3 log x. Okay, so if we leave that table open, we might add more to it as we go along. But there's a start point. So the idea of integration, going back to that previous slide, if we've got something like the integral of 3x, then we use the table of standard integrals. In this particular case, if there's no power to x, what will the power of x be? Right, so we think of that as just a 1. So add 1 to the power, divide by the new power, and we can integrate 3x, and so on. Okay? So let's just have a look at 1 or 2 and make sure we can use this table of integrals. Right, so let's look at some examples. 5 examples. So what I'll do is I'll just run down this so you can see them, and then have a go at them. So if you're looking at this video, pause the video and then have a go at them. Here are the answers. So number 1, integrate 5x with respect to x. What do I get? 5x 2 squared over 2. Yeah. Now, when you integrate, should have mentioned this earlier, whenever you integrate something, you're putting back a constant that might have disappeared when you differentiate. So this idea of undoing differentiation, if you remember when we differentiate a number, that disappears. So when we integrate to go back, there could have been a number. So we always add c at the end when we're doing an integration, if you remember, and I forgot that. So let's go back to our table of standard integrals and add that. Always plus c. Plus c, plus c, plus c, which I should have put in there. So add c to the end of each of your integrals on your table of standard integrals. So always plus c at the end. Yeah. Next one, integral of 5 sine 10 becomes? Yeah. Plus c. Yeah. Yep. Yep. Good. And we could simplify that a bit, couldn't we? Because 5 over 10 is a half, so minus a half. So minus a half cos 10t plus c. Next one, William. Next one. Add 1. So what we're going to do with this one, do it in 2 parts. So you integrate the first part with respect to x, and then the second part, and then put them together. So it could be the integral of 5x cubed minus the integral of 4x squared. So 5x cubed will be, yep, 5x to the power 4 over 4 minus the 4x squared will become, and then at the end plus c. Yeah. So it's just applying this rule. Number 4, what have I got to do to this one before I can do it? How do I rewrite that before I can integrate it? Nope. X to the 2 over 3. Okay. And now, same thing. So this can get a bit awkward, this one, because we end up with 2/3 plus a whole one, which is 5/3. Okay, yeah, you're right, Tom, but we write it as 5/3. And then we divide that by 5/3 and add c. Now, in examples like this, if you remember from last year, dividing by a fraction, you invert and multiply. So this becomes 3/5 of x to the 5 over 3 plus c. So that's something that often happens when we've got fractions. You've got to divide by the fraction. Excuse me, when you integrate, you've got to divide by the fraction, so then you invert that fraction and multiply. And you always do that. So with this number 5, the first step is to bring the t up to the top and call it a minus 2. And so now add 1 to the power. Minus 2 plus 1 is minus 1. And divide by the new power, which is minus 1. So it becomes 3. 3t to the minus 1 plus c, yeah. 3t to the minus 1 over minus 1 plus c. Okay? So that actually, tidying this up, the fact that it's minus makes the whole thing negative. So I can just say this equals minus 3. And again, t to the minus 1 can be written as 1 over t. So it becomes minus 3 over t plus c. So finally, one that can trip you up, if you just got a number and I integrate that, the variable, and in this case, remember the variable is t, so that's what that's telling us, becomes 5t plus c. This one's worth looking at because if we go back to differentiation, remember if I were to differentiate this, what happens? What happens to 5t if I differentiate that? The t disappears when you differentiate, gets you just to 5, so it gets this. And what happens to any constant when I differentiate? It disappears, and so we end up with 5. And this is the crux of the idea of what happens when we integrate something and why the c is added. Because often, and we won't be looking at this in this course, but often the idea is to try and solve a differential equation which involves a differential. So we integrate, and in this case where you've got a constant, the t reappears, the variable, and the c that disappeared when you differentiated again reappears. So that's that one, that's a special case. So the idea of definite integrals takes us into a use of integration. One use of integration is to find what the differential was that we started off with, to undo the idea of differentiation, which is very useful. But what we're going to look at now is another use of integration, because if I integrate a function between 2 points, and that's what this is saying, integrate 5x squared plus 4 between the limits 1 and 2, what that allows me to do is to find the area under the curve 5x squared plus 4 between the limits 1 and 2. So if I were to put this function 5x squared plus 4, which I've done in autograph here, What this is saying is that I can now integrate, if I integrate this function, I can find the area under the curve. So if I put this particular curve into my notes here, so what this is telling me I can do is, if I want to integrate this function 5x squared plus 4 between 1 and 2, what that's saying is I can find the area, the area underneath this curve between 1 and 2, which is this bit. And to do it, what I do is integrate the function using the table of standard integrals, and then put 2 in for x, work out what that is, 1 in for x, and then take the bottom limit away from the top limit, and that will give me this area underneath the curve. So it's useful for finding that, and we'll look at a practical example next week of how this can be useful to find the work done when we stretch a spring. So it's a very useful thing in engineering, this idea of integrating to find the area under a curve. So let's go through the method for this, and then I'll give you a chance to make the note. So what do I actually do in practice? So integrate this function between 1 and 2 to find the area under the curve between those 2 points, 1 and 2 in the curve here, 1 and 2. So what I do is look at my table of standard integrals. So I start off by writing down, integrate between 1 and 2, 5x squared plus 4 with respect to x. Now the notation is important here. What I do next is I integrate it. Integral of 5x squared, add 1 to the power, divide by the new power, 5x cubed over 3. Integral of 4, 4x, the x reappears. I don't put the c in because, as I'll discuss a bit later, because I'm subtracting one limit from the other, actually that constant disappears. So I've integrated it. Now, if this was an ordinary integral, I'd put plus c at the end. But because this is a definite integral, I now put a square bracket around the integral and put the limits in. So this is telling me, the notation is telling me, I've done the integral, but I've still got to put the limits in. And then I put the limits in. I put the top limit in first. So that means I rewrite the integral, and I put it in these curly brackets, but instead of x, I write the top limit, which in this case is 2. Oh, thank you. Minus, and then again I use curly brackets and I put the bottom limit in. So I rewrite the integral, but instead of x, I write 1. And then I work out what that is. So 2 cubed, 2 2s are 4, 2 4s are 8, 5 8s are 40. So that becomes 40 over 3 plus 8 minus 1 cubed is just 1, so that becomes 5 over 3 plus 4. And then I work out what that is, so calculator obviously you could use at this point, and end up with the integral, the area, which will be the area under the curve. The final answer turns out to be 15 2/3, which is the area under the curve. So what we're saying is this area here is 15 2/3. That area, 15 2/3. Yeah. Record this. So integrate the function 3 sine 4x between 0 and pi. So if we look at the function, if I type it into autograph, which I've done, here it is, and we go between 0 and pi, we notice one or two things for a start off. There's pi, here's 0. So if I integrate this function between 0 and pi, what I'm doing is I'm finding the area under the curve between 0 and pi. Now if you look at that area there, that's the area under this bit, area under this bit, and so on. So if I add them all together, what do you think the area under the curve will be? The area under that one, and then that one. What's different about that bit and that bit? Sorry? Yeah, so because... Correct, well done, Alex. That's plus, that's minus, so they'll cancel each other out. That's plus, that's minus, so they'll cancel each other out. So if I integrate between 0 and pi, I'll get 0, which is not very useful if I actually want to know what this area is. What do you think the solution is? No, no. Change my limits. What can I do to change the limit? 1 and pi? What, no, where's on here? Find your limits. What are these points on here? So if that's pi over 2. What's this point? Right, so what can I do if I want this area? Integrate between 0 and pi and 4, and then if I want the total area, what do I do next? No. So once I've got the area between 0 and pi by 4, I can then times by 4 and I'll get the area between 0 and pi. So particularly in trigonometric functions, which are symmetrical, then I have to take that into account. Okay? It's no good integrating between 0 and pi in this case because I get the answer 0. And if you wanted to do it, you can prove it. You know, I'll leave that as a little exercise for you to do. Integrate between 0 and pi and you should get the answer 0. So if I actually want the area, what I do is look at the function and choose my limits accordingly. So I'm going to integrate between 0 and pi by 4 and then multiply the answer by 4. Okay, so the note then, to do this integral, just to summarize this, that area is 0, as we can see, when we add up those 4 quadrants or those 4 sections, they'll add up to 0. So if we do want that area between 0 and pi, we change the integral to between 0 and pi by 4 here, and then multiply the answer by 4. So the integral becomes 0 and pi by 4, 3 sine 4x dx. The other thing to recognize about this is that this is in radians. So, yeah, make sure your calculator's in radians when you put the limits in at the end. So now the same as we did before, we do the integral. So what's the integral of 3 sine 4x? Right, and again we ignore c because when we put the limits in, we're going to subtract 1c from the other, so that disappears. But what we do is put that square brackets in between 0 and pi by 4. It's worth noting this. When you've got a constant in here, like the 3 over 4, what I'm going to do now is put this limit of x in, put pi over 4 and then a 0 in, and then subtract 1 from the other. So this 3 over 4 and minus 3 over 4 is common to both. So what I can do is take that outside. And then cos 4x between 0 and pi over 4. So that just makes the process a little bit more straightforward. Okay? So now, because I've left this, I've put this minus 3/4 outside, I've still got to leave that square bracket in there because I'm going to multiply the final answer by minus 3 over 4. And now, again, I put the limits in. What's the cos of 4 times pi over 4? Minus, what's the cos of 4 times 0, which is just 0. So this equals minus 3/4 cosine of pi, because the 4's have cancelled, minus the cosine of 0. at this point, you could get your calculator out and work it out. However, bear in mind this. If I were to write a cosine wave over one cycle, it looks like this. That's what the cosine wave looks like. It starts at 1 and finishes off at 1. The sine wave starts at 0 and finishes at 0, but this is the cosine wave. This is 1, and this is minus 1. And then, if we recognise that this, if that's one complete cycle, this is 2 pi. So halfway point, that will be pi. So what's the cosine of 0? 1. What's the cosine of pi? Minus 1. So what we have is, if you understand that curve and you can see that in your mind, which I'm hoping you will be able to, you could almost write down what they are. You don't really need to put it into a calculator. Of course, you can put it into a calculator and you get the same answer. So this turns out to be minus 3/4 of minus 1, which is minus 2. Minus times a minus gives a plus. So we've got finally 6/4, which is 1.5, or 3/2, yeah. So the area under that curve is 1.5, so therefore the total area equals 1.5 times 4, because remember we had 4 of those cycles, which is 6. So for the Unit 28 assignment, the past questions, let's have a look at the questions. So question number 1 is about differentiation. But I want to look at the function first, and it's also about thinking about what the differential tells us about the function. Remember, the differential tells us the rate of change of the function, which is the gradient of the function. So for this particular function here, I want you to plot the function using autograph, and then find the rate of change of this function after 1 second. So that means what you're going to do is you're going to differentiate it, and then put in the value for 1 second and find out what the differential is after 1 second. Find the rate of change after 1 second. Number 2, the shape of a mechanical component in a system is modeled by that function. Again, you could differentiate that, put that function into autograph and see what that shape looks like. But what you've got to do is differentiate this function and then express your solution in its simplest form. So if you look at these, you've got combinations of functions. So you're going to have to use the rules, the quotient rule, the product rule, and the chain rule to do these. The last question, find the rate of change of that function below, again, after half a second. So 3 questions. It wouldn't be a surprise, would it, that you've got one of the products, one of the quotient, one of the chain rule, okay? Then you get to question number 4, which is something that we're going to have a look at in a bit more detail next week, which is the start of the integration. You're going to find out the constant of integration and what these constants are in the function. And then number 5 is something you may want to have a look at today if you get that far. It's asking you to find the average value of a voltage waveform using integration, which is finding 1/pi times the integral between 0 and pi of that function. But we'll look at those 2 questions in a bit more detail next week. Okay.